So I mentioned just quickly before that I will be writing code in CMake projects. Now, I just want to quickly talk about this link here before I get into this recap. So this link in the slides will actually take you to, if I copy it across the right screen now, this here. So this will be the, well, this is going to be the repository, but more so I have in my GitHub a Git tutorial repository, and in here I go through quite in depth. This is for my students at TUM, where I explain to them the compilation process more in depth than I will probably in this lecture, because I've written pages and pages of text going through it very much in detail. Also sort of talk about CMake, which is a build system or build tooling framework, what have you, for implementing or for constructing C projects, or actually not just C projects, but constructing builds for code, and I'm using it for C. And so I'll be using CMake to generate my build files and my make files and inevitably build my code. So I'm not going to be using just standard GCC calls, because I come from a younger generation and I really don't use GCC very much in my life. So for those who are not quite sure what's happening with the CMake, I would recommend you maybe take some time, go through this tutorial. If you're a really motivated student and you haven't really had any exposure to Git, and you're a computer science or enthusiast in computer science, and for really anyone that's going to be writing code in their professional career should probably know what Git is. My students give me good feedback on this tutorial. It's quite a lot of reading, but I really try to give you a good in-depth explanation of Git and building and some other sort of concepts in C development. And hopefully at the end of it you have a pretty good idea of what's happening. So that's the tutorial. Let's put this back on the right screen. So we'll put this back here. So now back to the lecture. So in the introductory lecture, for those of my SIT students, I quickly talked about the compilation process. Now, it could be a bit misleading saying compilation process, because compiling, or like the compilation of C files, is really only one step in the process. Now, the entire building of a program, like the building of an executable file, comprises of three sort of steps. We have the pre-processing, which we can see here. If we go down to the next slide. Why are you not moving? Next slide, please. So you have the pre-processing, and so this is where the C files, with all of their sort of hash defines, hash includes, macros, comments are taken out. All of this it's really on a pure text basis. These files are passed by the preprocessor, and these preprocessor directives are completed. Hash defines are replaced with their values, macros are expanded, includes are sort of copied and pasted, which we'll get into a bit further in this lecture series, and the comments are removed because comments don't really compile to anything useful. So this is the preprocessor, which takes your raw C and header files and creates essentially a set of files that can be then compiled. So this is sort of like the preprocessed file. So then if we go down to the compiling, so compiling is really just a step of the build process where the C and header files, and pretty much just the C files, are actually compiled by a compiler. So I'm on an Arch Linux system, or really on NX Linux system. You'll probably be using GCC, so the GNU compiler, and the compiler will take each C file and turn it into an object file. Now these object files have references to functions or objects, whatever variables that are found in other C files. And so this is the problem. This is the last step, where these object files are brought together to create an executable binary. And so this step is the last step, where we call it linking. And so it takes all of these object files, which we can see here. These guys, take my pen. So they create these object files here, and this is the output, and these are put together to link to create some sort of an executable file. This could be an ELF file, a hex file if we're dealing with embedded systems, a binary file on a Windows system, to be an exe file, I think they are. And so this is the final step, where we take our separate object files that might actually reference each other, and we put them into one sort of homogeneous binary that can execute. And this is also where we might come across where you have to link against library files being ones that you've compiled yourself, if you're compiling a static library for your project, or ones that you find in your system, such as libxml or libssh or something like this, where you're using the functionality of these libraries, but you don't want to include the library's actual sources in your project. Then you just say, hey, yep, I'm going to assume this is on a system that has these libraries and will link against them, so that at runtime it will try and find the functions, the references in the existing library files on the system. So this is the quick recap of the compilation. I've talked about this in my introductory lecture. I would also recommend to then, for anyone that really wants to know a bit more about this, to go and read my Git tutorial, which actually, by doing so, explains very much in depth the compilation process. So now, quickly to summarize before we go into C and talk about all the different sorts of syntax and what this is, what that is, and how you actually use the language, just a quick summary of the language itself. So why C is such a powerful language, and it's also very predominant in the world of computer science, and especially in embedded systems, operating system design, meaning kernels, device drivers, and these sorts of things. Oh, I should move my screen over. Yeah. Wait. Sorry. And so why it's such a popular language is because it's very general purpose, like this first point says. It's portable, meaning that it is able to be compiled. I can take my program, compile it. If it's a simple program, like it doesn't really do anything too amazing, I could take my simple program, compile it on my laptop, run it on my laptop. I could probably take the same program, compile it, and run it on an embedded system. I could take the same program, compile it, and run it on my toaster. So really, it's a very powerful language for people who want to write low-level code and also code that they can take and run on many devices. And so this is why C is generally the picked language for the world of embedded systems, even though we're finding trends to go towards interpreted languages like MicroPython, blah, 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 which really have a lot of overhead. But C is in my eyes, the king of programming languages, in that it's the most versatile and most powerful. It's a lot of work sometimes, but it's a very good language. So it's quite an old language. It's very well established now. Originally, as the language that came after the B language, and it was developed in 1972. So I mean, you've got almost 50 years of history here in the language. And so one thing that's very good about C, and why I personally like it being my favorite language, is that it's extremely structured. I mean, you're using data structures, memory structures, to perform very efficient and fast code, meaning with Python and these sort of interpreter languages, or JavaScript and all of these web languages, you have some sort of an interpreter that actually reads in a script and interprets it at runtime. But C is a compiled language, and also a very low-level compiled language, meaning that it's compiled down into like machine code essentially, and it can be highly optimized for processor architectures, just general software optimizations, memory usage, and all of these sorts of things. So it really is a great and powerful language, while it does have drawbacks in that you don't have the sort of, it's harder to achieve the high level of abstraction that you get in languages like Python and Java and JavaScript and these, right? But the upside of it is that you have really the ability to write low-level applications. So you can write embedded systems, direct access. I should probably move my face out of here. So you can see here, direct manipulation of hardware. And this is really good for embedded systems, where you need to communicate with an Ethernet controller that's on the board or some sort of peripheral. And this sort of leads to then the next step up for an embedded system, meaning an OS kernel, so such as the Linux kernel, which is written in C. You're writing device drives to talk to the webcam I'm using, the pen I'm using with my laptop. These are all device drivers written in C because they have access to the hardware. And so this is why it's such a great language for those people that are interested in this sort of hardware, software meeting point in the computer science, electrical engineering world. So now I'm going to go into the first topic, which is just the general program structure, and I'll get into that in a second.